Section 14.7, Maximum and Minimum Values. A function of two variables has a local maximum at ab if f of xy is less than or equal to f of ab when xy is near ab. The number f of ab is called a local maximum value. If f of xy is greater than or equal to f of ab when xy is near ab, then f has a local minimum at ab, and f of ab is a local minimum value. So in other words, if we're looking at a particular point and it's bigger than all of the nearby points, then it must be a local maximum. And if we're looking at a nearby point, or if we're looking at a point and all the nearby points are bigger, so the point that we're looking at is smaller than all of the nearby points, then it must be a local minimum. And then if these inequalities hold for all points in the domain of f, then it must be an absolute maximum or absolute minimum, pretty much the same way as we saw in single variable calculus. Then we have a theorem that if f has a local maximum or minimum and the first order partial derivatives of f exist there, then they must both be 0. So to prove this, it's pretty much just applying Fermat's theorem from when we did maximum and minimum values in single variable calculus. We let g of x be f of x where b is a constant y value. So now it's a single variable function. If f has a local maximum or minimum at the point ab, then g has a local maximum or minimum at a, so g prime of a equals 0 by Fermat's theorem. But g prime of a is just the partial derivative of f at ab with respect to x, so that partial derivative must be 0. It pretty much follows because we take partial derivatives by holding one of the variables constant, so we get a single variable function. So in single variable calculus, having the a local maximum or minimum forces the derivative to be 0. So it should make sense that having a local maximum or minimum forces partial derivatives to be 0, because partial derivatives are basically just derivatives where one of the variables is constant. So we can also do the same thing to the function g of y, where we set x to be the constant a value, and applying Fermat's theorem gives us that the partial with respect to y is also going to be 0. So next up we have a definition. A point ab is called a critical point or stationary point of f if the partials are both 0 or if one of the partials does not exist. Pretty much the same as it was for single variable critical points. So how about we do an example and find the extreme values of this multivariate function. So let's look at the partial derivatives. The partial of f with respect to x of xy is 2x minus 2, and then the partial with respect to y is 2y minus 6. So let's look for where those guys are 0. So the partial with respect to x is 0 when x is 1, and our partial with respect to y is 0 when y is 3. So that means that 1, 3 is a critical point, and I'll just write CP for critical point. So that means that we're looking at f of xy equal to this thing in order to see whether the critical point is a maximum, minimum, or anything. We should probably try to look at the characteristic of our function because we don't really have another way yet. So how about we complete the square? I've got x squared minus 2x. So I'll add half of minus 2, which is minus 1, squared is 1, and some adding and I'll subtract it. So I'll have 14 minus 1, and I'll do the same thing for the minus 6y. So I will add and subtract half of 6 is negative 6 is 3, and then squared is 9, so it looks like I'll just subtract 10 from 14, so I'll get 4 plus x minus 1 squared plus y minus 3 squared. And you can try writing that out to complete the square if you're not convinced. So it looks like the smallest this could possibly be is 4. Because both of these guys are greater than or equal to 0 because they're both being squared, so there's no way there could be any negative values there. So there's no way we could make 4 any smaller than it already is. So the fact that x minus 1 squared is greater than or equal to 0, and the fact that y minus 3 squared is greater than or equal to 0 implies that our function f of xy is always greater than or equal to 4. It's greater than or equal to 4 for all xy. So that means that f of 1, 3, which is equal to 4, must be a local minimum, because that's the smallest it could possibly be. So if we were to graph this thing, notice that this is like 4 plus x squared plus y squared equals z. So that's just like y equals x squared, but in 3 dimensions. So it's an elliptic paraboloid. It's like our 3-dimensional parabola shape. So it looks roughly something like this. And if we were to trace this way, we would get parabolas. If we were to trace this way, we get ellipses. And I should probably throw this in the xy plane, xyz plane. Not plane, 3-dimensional space. So we'll throw all of these guys in there, and then here's our point 1, 3, 4. So you can confirm this visually. It's definitely a minimum. In fact, it's the smallest point for the entire graph, so it's an absolute minimum even. How about we find the extreme values of this function? So we'll take the partial derivatives again. So we get the partial derivative with respect to x is negative 2x. The partial derivative with respect to y is 2y. So it looks like these guys are both 0 when x and y are 0. So that means that 0, 0 is a critical point. So let's see what that critical point is. Well, how about we look at points nearby? So if we look at points nearby, let's say on the y-axis, then we're looking at points where x is 0. So that means that f of xy becomes minus x squared, which is negative, provided that x is not 0. If we, however, look on the x-axis, then we have y equal to 0. So f of xy is going to be y squared, which is positive, provided that y is not 0. So it looks like if we look around the point 0, 0, our critical point, we have some positive values and some negative values. So this means that f takes on positive and negative values in, say, every disk, every cluster of points that's centered around the origin. It looks, let's say something like this. Say I draw the disk. So this is, let's say, in the xy plane, and here's the origin in the center. Then we've got some points on the y-axis. If I would look at the z value, it would actually be negative, so it would be below this plane. If I would look at the z value, however, along the x-axis, those would be positive. You could imagine these z points floating above on the left and right. So it looks like there is, or f of 0, 0 is not an extreme value, because there are some points around that are bigger and there are some points that are smaller. So it's not the smallest and it's not the biggest. So that means that f has no extreme values, because that was our only critical point. So it would be nice if we didn't have to go through this every single time and look at a disk and look at nearby points to try to figure out if our values are extreme values or not. And in fact, we have a second derivatives test for multivariable calculus similar to the way we had it in single variable calculus. It's a little bit more complicated though. So suppose we have second partial derivatives of f, they're continuous on a disk with center AB, and suppose that each of the partials is 0, then we let d as a function of the point AB equal to the partial derivatives, the second partial derivatives of f with respect to x with respect to y, multiplied, and then we subtract the mixed partials squared. If this number that we get when we do this for d is positive, and our second partial with respect to x is positive, then we have our value of our function at AB as a local minimum. Remember, in single variable calculus, that was when we had something concave up. That was when our second derivative, f double prime, was positive, so it makes sense that it should be a local minimum. We only need to look at one of the second derivatives, because notice we're assuming that d is positive. The only way for d to be positive is if both of these guys have the same sign. Because if this thing is positive and this thing is negative, then this would be negative and we'd be subtracting something, so we'd potentially have something even more negative, because subtracting a positive number from a negative just gives you an even more negative number, but we're assuming that d is positive. So if one of our partials is positive, the other one will be too, so it makes sense that we should have a local minimum there because all our partials positive. If d is positive and this guy is negative, then we're saying, again, these guys have to have the same sign because this has to end up as a positive in order for d to be positive. So we're saying that it looks something like this, where it's going to be sort of concave down, where our second derivative is negative, but in terms of partial derivatives, so they're all going to be negative. So that gives you a local maximum. If, on the other hand, d is negative, then we're saying that either we have mixed partials, in which case one of these is positive and one of them is negative, or in that case one of the other partials is positive or negative, because this would just have to be subtracting off more than whatever this value is, and in that case f of AB is not a local maximum or minimum. This is a little bit harder to see. So in order to prove the second derivatives test, what you really do is you take a look at the directional derivative, because if the second derivative test works, you're basically testing the directional derivative in every possible direction, and if the directional derivative is consistent, it's consistently, for example, positive, then you know that you have a local minimum, because it's almost like you're concave up everywhere. Whereas if your second derivative or your directional derivative for the second derivative is negative everywhere in every direction, then you have a local maximum. But if your directional derivative is sometimes positive and sometimes negative in certain directions for your second derivative, then you know that you have neither a local maximum or minimum, because you've got some points that are bigger and some points that are smaller, like in the previous example. However, if d is equal to 0, then the test gives no information whatsoever, because in that case it's possible that we have the same sign over here, and it just happens to cancel out perfectly with this over here, or it's possible that the sign is different for one of these guys, or the sign is different for another directional derivative and it just happens to cancel. So it could be that you have a local maximum, it could be you have a local minimum, or it could be that you have what we call a saddle point, when you have neither a local maximum or minimum, but you just don't know. So we only know if d is greater than 0 or d is less than 0. If d is equal to 0, then we have to get more creative to figure out what the point could be. We can't assume that it's going to be anything. It's sometimes helpful to look at d as the determinant of this matrix over here called the Hessian as shorthand, and that way you can remember this formula that looks kind of long but isn't actually that long. It's just cross multiplying these components of this matrix over here, and then subtracting the same way that we get determinants of 2 by 2 matrices. Let's do an example and find the local maximum, minimum values and saddle points of this function. So we will look at the partial derivatives. So with respect to x, that's 4x cubed minus 4y. With respect to y, that's 4y cubed minus 4x. So we're looking for where these guys are 0. So that's where x cubed minus y is 0, and where y cubed minus x is 0. So how about I solve for y over here? So I get that y is equal to x cubed, and then I can substitute that in over here, and I'll get 0 is equal to x to the 9th minus x, which is x times x to the 8th minus 1 when I factor. And then I can keep factoring and get x times x to the 4th minus 1 times x to the 4th plus 1, because that's a difference of 2 perfect squares. But then I have another difference of perfect squares, so I can factor that as x squared minus 1 and x squared plus 1. And I still have my x to the 4th plus 1. So it looks like I have 0, 1, and minus 1 as our x values for when this function is 0. And those give me my critical points. So I plug that in to get y, and I see that 0, 0, 1, 1, and minus 1, minus 1 are our critical points. So how about we look at the second partials to figure out what each of these are. So the second partial with respect to x is 12x squared. Just differentiate that, y is constant. And our mixed partial, we'll do with respect to x and then y, is minus 4. Remember, we never need to get the other one, y and then x, because they're going to be the same by Paraboloid's theorem because these guys are continuous. So we just get that fyy is 12y squared, and now we're in business. We can get that our determinant of our Hessian matrix D is equal to fxx fyy minus fxy squared, which is 144 x squared y squared minus 16. So let's look at it at each of our points. So it's 0, 0. If I plug that in, then I get 0 minus 16, so that's minus 16, which is negative. Since it's negative, we're guaranteed that 0, 0 is a saddle point. It's neither a local maximum or minimum, or neither brings about a local maximum or minimum. And then we'll look at 1, 1. So plugging that in, we get 144 minus 16, which is 128. So that's positive. We also see that our second derivative with respect to x at 1, 1 is 12. So that's also positive. So that means that we have a local minimum. So f of 1, 1 equal to minus 1 is a local min. Imagine it's concave up over here. So then we've got minus 1, minus 1. And plugging that in, they get squared, so we still have 128. So this thing's still positive. And notice that our second derivative also has everything squared, so at minus 1, 1, that's still going to be positive also. So that means that f of minus 1 is also equal to minus 1, and it's also a local minimum. So this is kind of cool. If we were to look at a graph of this, it should look, let's see, something like this. Not that great, but that's okay. And maybe I'll throw in a z-axis. And a y-axis. And x. So it looks like it's like kind of a pair of pants, or maybe Patrick Starr's feet. But in any case, here are our local minimums. We have two of them, both at z values of -1. One's at f of 1, 1. One's at f of -1, -1. And over here is our saddle point. Notice that it goes up a little bit if you look at nearby points, but it also goes down a little bit if you look at nearby points. So it's neither a local maximum nor a local minimum. Next up, let's find and classify the critical points of this function. So we do it the same way. We look at the partial derivatives. So we get that with respect to x, we get 20xy minus 10x minus 4x cubed. And then the partial with respect to y is 10x squared minus 8y minus 8y cubed. So how about I take this guy and I set it equal to 0, and I factor out the 2x because that's everywhere. So I get 2x times 10y minus 5 minus 2x squared equals 0, and for this guy there's nothing to factor out, so I'll just get 5x squared minus 4y minus 4y cubed equals 0, because I'll just divide by 2. And 0 divided by 2, it just disappears. Okay, so how about we look at when x is 0? Because that makes this guy 0, right? Just kills the whole thing off. So that's one possibility. Our other possibility is that this thing is 0. So we could also have 10y minus 5 minus 2x squared is equal to 0. All right, let's look at each of those possibilities individually. So first, let's look at when x is 0. So if x is 0, then I plug that in over here for this x in the second equation, and I get minus 4y times 1 plus y squared equals 0. So that means that y is 0, because this can't be -1 because it's being squared and we're in real numbers right now. So we have y equals 0, so that means that plugging that in we can get x is 0 also, so 0, 0 is a critical point. So we found one critical point. Let's look at our other possibility now. Let's look where this would be 0. So if 10y minus 5 minus 2x squared is equal to 0, then we can just solve for x squared. We get that x squared is equal to 5y minus 2.5. And how about we take what we have for x squared and we plug that in for x squared in the second equation now. So we'll replace that x squared with 5y minus 2.5, and we'll simplify, and we get that 25y minus 12.5 minus 4y minus 4y cubed is equal to 0. So that's the same thing as saying 4y cubed minus 21y plus 12.5 is equal to 0. So if you know the cubic formula, you could solve this. Otherwise, we'll just use our handy-dandy calculator emulator and find the roots. Go to y equals, we'll type in 4x cubed, because I'm just going to use x instead of y to plug in, because it doesn't matter, minus 21x plus 12.5. There's my graph. It looks like I've got 3 real roots, so I'll do second trace to get to the calc menu, and I'll look for the zeros. So left bound, so how about we go, that's fine, I can go to -3. and then I'll go to the right of the 0. There we go. And then I'll guess it's over there somewhere. Looks like my first one is at negative 2.542 about. And remember, it says x, but where I replaced that, these are y values. Okay, let's get the next root. So go a little bit farther. Okay, and I'll go to the right of it. Okay, and we'll guess it's somewhere over there. Alright, so my second root is 0.6468 about. Let's get the last one. Yeah, whatever, it's fine. I can go all the way to the left over there, as long as I go to the right over here. And I'll say the root's somewhere over there. Okay, so 1.8984 about. Great. So let's write those in. So we have that y is about negative 2.5452 about 0.6468 was my second one, and about 1.8984. So remember that we said that x squared is equal to 5y minus 2.5, so x is equal to the plus or minus the square root of that. So that means that I could write x equals plus or minus the square root of 5y minus 2.5. So if I plug in this negative y value over here, then I get negative inside the square root. So I'm not allowed to do that. So I can only plug in these two guys. So if I plug in this, then I can use a calculator and see that x is about plus or minus 0.8567. And if I plug in my other y value, I see that x is about plus or minus 2.6442. So it looks like we got two x values for each of our y values, and we have that critical point that we already got, 0, 0. So we now have 4 additional critical points, so we have 5 critical points. So how about we make a nice little table of all our critical points and what each one is. So I'll have my critical point. I'll have f, the value of my function. I have f(x)(x), the value of my second derivative. I have the value of d over there, and then I'll figure out what each of those things is. So for the critical point 0, 0, if I plug that into the function, I get 0. So I'll write that as 0.00 because I'm going to have to round for the other ones. If I plug that into the second derivative, I get negative 10. And then if I go and compute d, which you can do separately, you should get 80. So that means that we have a local maximum because d is positive and our second derivative with respect to x is negative. Okay, how about our other critical points? So we can look at plus or minus 2.64, 1.90 at the same time because, and I rounded a little bit more, notice, because they both have the same y value, or z value in this case, actually, of 8.50, and they both have the same second derivative value of negative 55.93, which results in the same d of 2488.72. So again, we have a local maximum. So it looks like so far we have 3 local maximums because there's 2 of them over here that I did at once. Then lastly, we take a look at plus or minus 0.86, 0.65. F in this case is negative 1.48, and fsx is negative 5.87, and d is negative 187.64. Because d is negative, we have a saddle point. So we have 2 saddle points and 3 local maximums. Notice you have to be a little bit careful. I got kind of lucky here that I have the same values for both of these points at plus or minus, but that doesn't always happen, so usually you have to look at each of these points separately. Next up, let's find the shortest distance from the point to the plane. So we did this in section 12.5 using vectors, but here's an alternative method using our second derivative. So we could say that the distance d between a point x, y, and z and our point 1, 0, minus 2 is x minus 1 squared plus y minus 0 squared plus z minus minus 2 squared, so z plus 2 squared, and then we take the square root. So we have z equal to 4 minus x minus 2y. So how about I just plug that in for z so that I have a function of 2 variables. And that way I can actually do my partial derivatives the way that I'm used to. So I have x minus 1 squared, and I've got y squared, and then I've got 6 minus x minus 2y squared, because the 4 becomes a 6 when I add 2. As we saw in section 4.7, I think it was example 3, when maximizing or minimizing, in this case, the distance d equal to the square root, that's the same thing as minimizing d squared, which is going to be our f of xy, and that's a lot easier. So that's just x minus 1 squared plus y squared plus 6 minus x minus 2y squared. So our partial derivative with respect to x is 2 times x minus 1 minus 2 times 6 minus x minus 2y. So that's 4x plus 4y minus 14, and we want to know when that's equal to 0. Similarly, for our partial with respect to y, that's 2y minus 4 times 6 minus x minus 2y, and that's equal to 4x plus 10y minus 24. I want to know when that's equal to 0 also. So solving this over here isn't too bad. You should get pretty quickly that x is 11 over 6 and that y is 5/3. So that's our critical point. So let's look at the second partials to see what that is. So second partial with respect to x is 4. Our mixed partial is also 4. And our second with respect to y is 10. So we look at our determinant of our Hessian, and we get that that's fxx minus, or sorry, I have to multiply first, fyy minus fxy squared. So that's 24, which is positive. We also have that our second partial is constant 4, which is positive. So that means that we have a local minimum. So f has a local min at the point 11 over 6, 5 over 3. You can also argue from the context of the problem there has to be a minimum distance somewhere. And we only had one critical point, but that's okay. We'll just set d equal to the square root of x minus 1 squared plus y squared plus 6 minus x minus 2y squared, and that's equal to 5/6 squared plus 5/3 squared plus 5/6 squared. So that's 5/6 rad 6 as our minimum distance. Okay, say we have a rectangular box without a lid, and it's to be made of 12 square meters of cardboard. Let's find the maximum volume of such a box. So it looks, I don't know, something like this. Here's our box, try to draw it. Roughly boxy. That looks sort of like a box. And it's got no lid. I don't know if I can draw it that. It's not so easy. But, do my best. Okay, so we can look inside the box. How about we call this x, this y, and this z, so those can be the dimensions of the box. So our volume is x, y, z, and we want to eliminate z as we did before because we just want two variables in our function. So how about we look at the surface area of the box. Notice that we have z times y in the front and back, so that's 2zy. We have x times z in the front and back, so we have 2xz, but we only have one of the xy's because the top is open. So our surface area is 2xz plus 2yz plus 1xy, and that equals 12. Because I told us it'd be 12 square meters. So we solve for z, and we get that z is equal to 12 minus xy divided by 2 times x plus y. So we can rewrite our volume now in terms of two variables. So that's going to be x times y times 12 minus xy over 2 times x plus y. So that simplifies to 12xy minus x squared y squared over 2 times x plus y. So how about we look at the partial derivatives? We want to see where that's 0, so the partial derivative of the volume with respect to x is y squared times 12 minus 2xy minus x squared over 2 times x plus y squared. And let's look at the partial derivative of the volume with respect to y. So that's x squared times 12 minus 2xy minus y squared all over 2 times x plus y squared. So we'll set these equal to 0, so we want to know when the numerators are 0. Notice that if y squared and x squared is 0, then the dimensions of our box are 0, so we have a volume of 0, so that's useless. So how about we just consider where these guys are 0. So that's where 12 minus 2xy minus x squared is 0, and that's where 12 minus 2xy minus y squared is 0. So notice that we can set these guys equal to each other and cancel these out. So we get minus x squared equals minus y squared. In other words, x squared equals y squared. And that means that x equals y, because we're assuming that x and y are both positive, so that we don't have any negative or 0 dimensions here. Alright, so x equals y. We also have that 12 minus 3x squared is equal to 0 then, because I can just replace y with x over here, and I get minus 2x squared minus x squared is 3x squared. So that means that x is 2, and x is equal to y, so y is also 2. So now I can write that c is equal to, we solve for it over here, so I'll plug in 2 and 2, so I get c is 12 minus 2 times 2 divided by 2 times 2 plus 2, which is 1. So our volume is 2 times 2 times 1, which is 4 cubic meters. Next up, we have to talk about the extreme value of theorem a little bit, because it turns out that there's one for functions of 2 variables also. But remember that the extreme value theorem relied on having a closed interval in our domain. But in this case, our domain is in R2, so we need to talk about what it means to have a closed set in R2. And we'll define that as one that has all of its boundary points, where a boundary point of D is a point AB, such that every disk with center AB contains points in D that are also points, contains points in D and also points not in D. So for example, if I were to draw a point over here in the boundary, and I look at a disk nearby, then I've got some points not in there, and I got some points that are in there, which is not true for points inside, where they only have points in there, and also not true for points outside, where they only have points out. Okay, so these sets are closed sets because they contain all of their boundary points. Over here, we use this dashed line to indicate that it does not contain all of its boundary points. So this set is not closed, and this set is missing one boundary point. In this case, this set has all of its boundary points in the bottom, but not on the sides, where they're all dashed. So we've deliberately not said that these sets are open, because it turns out the opposite of closed is not open. And so we'll just say that they're not closed. You might see that later on in topology explained a little bit more. So we now have an extreme value theorem for functions of 2 variables. We say that if f is continuous on a closed bounded set in R2, then f contains an absolute maximum value, f of x1, y1, and an absolute minimum value, f of x2, y2 at some points x1, y1, and x2, y2 in D. Okay, so to find the absolute maximum and absolute minimum values of a continuous function, we need to look at the critical points. We need to look at the extreme values on the boundary, because it could be similar to what we did in single variable calculus. It could be that if we have some crazy function, that the maximum is, let's say, at an endpoint, or it could be that the minimum is at an endpoint, or it could be that the minimum is somewhere in the middle, not at an endpoint. So we need to check all of those critical values in the middle, and we need to check those endpoints. But in this case, there's tons of endpoints because they're all along the boundary, because we have a 2-dimensional set now for our domain. So we have to look at all of those different points. Okay, how about we do an example and find the absolute maximum and minimum values of this function. So since it's on a rectangle, we're guaranteed that there will be absolute maximum and minimum functions by our extreme value theorem. Notice that this rectangle is closed because we have it equal, so it includes all of its boundary points. It is also bounded, because we could just draw a disk around the rectangle if we wanted to. So how about we look at the partial derivatives? We've got the partial derivative of f with respect to x equal to 2x minus 2y. We want to see where that's equal to 0, and we want to see where fy equal to minus 2x plus 2 is equal to 0. So we can just add those together to see that y is equal to 1, so 1, 1 is a critical point. Pretty easy to eliminate x. And that means that we're looking at f of 1, 1 equal to 1. So we also need to check all along our boundary. We have one critical point, but we've got tons of other points along our boundary to check. So how do we draw a boundary? So it's this, we are in the xy plane, and it's going to be this rectangle. So here we are at the origin, and then x goes to 3, so this is 3, 0, and y goes to 2, so this is 0, 2, and this corner then must be 3, 2, because we're just relying on this over here. How about we label this part of the boundary line number 1? We can call this one line number 2, and this one we can call line number 3, and this one we'll call line number 4. So let's look at each of those separately, because there's an infinite number of points that we have to check now along each of these lines. So how about we do line 1 first? So in that case, notice y is 0 there, which is along the x-axis. So we're looking at f of x with 0 plugged in for y, which is just x squared. And x goes from 0 to 3. So notice that's just the parabola y equals x squared from 0 to 3. F of 0, 0 equals 0 is a minimum. And f of 3, 0 equals 9 is a maximum. You can also see that because x squared is increasing, so its minimum must be at the end 0 and its maximum must be at the end 3. Alright, let's look at line number 2. So that's when x is 3, because x is constant over here and y is going up from 0 to 2. So we're looking at f of 3 plugged in for x and y, and that's 9 minus 4y. And y goes from 0 to 2. So this function is decreasing. So that means that we started our maximum and we ended our minimum. So we could say that f of 3, 0 equals 9 is our maximum along this line, and f of 3, 2, which is 1, is our minimum. Alright, we got 2 more lines to check. Let's do number 3. So for line number 3, we have y is 2, that's a constant. So it looks like we're looking at f of x with 2 plugged in for y. So that's x squared minus 4x plus 4, where x goes between 0 and 3 still. So what we could do is we could factor this as x minus 2 squared. So this is a parabola opening up with vertex 2, 0. So that's got to be our minimum. So we're looking at f of 2, 2 equals 0 to be our minimum, because plugging in, notice this can be never be negative because it's being squared, so the smallest it could possibly be is 0, which is when you plug in 2. And as far as a maximum goes, this thing will be the biggest when what's inside over here has the biggest absolute value. So notice that happens when you plug in x equals 0, because then you get minus 2 squared is 4. Plugging in anything else in this interval will not make this thing as big as it would be for when you just have minus 2 being squared. So we have f of 0, 2 equals 4 as our maximum value there. Alright, one more line. We've got L4 now, where x is 0 because this is where we are. And we're looking at f of 0y, which is 2y. And y goes between 0 and 2 again. So we see that f of 0, 2 equals 4 is our maximum. Because again, this is an increasing function, so it happens, the maximum happens at y equals 2. And we also see that then f of 0, 0 when y is 0 must be a minimum. So let's look at all of our different possible possible extreme values. We've got our critical point at 1, 1, where f of 1, 1 was equal to 1. We've also got when z was equal to 0, equal to 9, 9, 1, 0, 4, 4, and 0. So it looks like the biggest value it could possibly be was 9. And it looks like the smallest value it could possibly be was 0. So notice that one of those happened not in any of the corners even, it happened inside of the line L3, because we ended up with f of 2 being 0. So that's somewhere over here. So we can say that we have an absolute maximum value at 9, which happened at f of 3, 0 in both of these cases. So we can write that our absolute max value of f on our domain D is f of 3, 0 equals 9, and our absolute minimum value of f on our domain D is f of 0, 0, which is the same as f of 2, 2, which is interesting. And that's equal to 2. Oh, sorry, that's equal to 0. Notice that in this case, our absolute max and min did not happen at a critical point. It didn't even happen at the point that we found from looking at the partial derivatives. It happened along these boundary lines. So you must be very careful not to stop after you check partial derivatives. If you have a closed and bounded domain, you must check for absolute max and mins on the boundary.